Hello and welcome back to our class after an extended break. Today we're going to be covering Section 3. And Section 3.4 is going to be on a new type of limit called limits at infinity, which will also be related to horizontal asymptotes. And then at the end we will also talk about slant asymptotes. Oh yes, calculus. Back at it, aren't we? Okay, so the first thing we're going to talk about is the new type of limit called the limits at infinity. And recall, the basic idea of a limit was that a limit is an operation that tells you something about the function. So it typically gives you a number out. So in the past we've dealt with regular limits, so this two-sided limit tells us what the output of the function is approaching or tending towards as we send our input close to the number c. And the reason limits are useful is because this can make sense even though the function itself doesn't make sense if we actually plug in the number c here. So our new type of limit is we're basically, instead of having a number that we're taking our limit at, we're taking the limit at either plus infinity or minus infinity. And essentially what this is going to tell us is what happens to the function as we plug in larger and larger inputs. Okay, so basically we're going to be asking what do the outputs of f of x tend towards as x gets very large, or as x goes to infinity. And a nice way to think about this is very often in applications we can think of a limit at least positive infinity as what happens in the long run, or what happens if you were to wait a long time, what would the outputs approach. So as a simple example, if we take a open tank of water and we imagine it was filled with water, and we leave it in the desert for a long time, and as a model we might take v of t to be the function that gives the volume of the water in the tank at every time t. Then after you wait a long time, the water slowly evaporates out of your tank of water, and so we would expect that the limit of the volume as t becomes progressively larger and larger, or as we wait longer and longer, to be 0. So in terms of a graph, we might expect it to look something like this. So the idea might be that at some initial time, 0, we have some initial volume of water, which should be the volume at time 0. And then as we leave it in the desert, it gradually starts losing its volume of water, and so it starts going closer and closer to 0. And maybe it takes a while to actually get there, or maybe it even eventually just actually equals 0. And so what we're looking at is, as we send our outputs farther and farther to the right, what is happening to the outputs of the blue line? And we see that they're decreasing and they're approaching an output of 0. And so yes, we would expect that the limit of v of t as t goes to infinity to be equal to 0. And this is the idea of an infinite limit. Okay, so as an example involving an equation, we have this function. So we are interested in finding what the limit of this function is as t goes either to infinity, which means we go out really far to the right, or as t goes to minus infinity, which is the same idea, but we go really far to the left towards negative infinity. So the graph here looks something like this, is a plot of it. So the green line here is your f of x. So the green line is f of x. And this blue line is what we will later call a horizontal asymptote. And so it's not actually part of the function, but what we see for this function 3 plus 1 over t is that as we plug in inputs, maybe we start by plugging in a value here, we get an output up here somewhere, but then as we move farther to the right, these outputs, they're decreasing. Maybe I plug one farther out, I get a little bit smaller, but they're not decreasing forever, right? So the outputs are approaching this blue line, which is the number 3. So in this case, we would expect the limit as t goes to infinity to be 3. And similarly, if we go in the opposite direction, if we start thinking about outputs moving to the left, this output's a little less than 3. I plug something a little bit farther to the left, it gets a little bigger. Something closer to 3, but still less than. We go out a little farther, and so on. And we imagine if we kept going out farther and farther, it just keeps getting closer and closer to this number 3. So we say that the limit as t goes to minus infinity. And so we expect that this one should be 3, and this one should be 3 as well. Turns out that these can be different, but in this case, they're both the same number. So what we were saying is that from the graph, that for larger and larger inputs t, the outputs get progressively closer to 3 and never gets farther away. That's an important point. We can always find an output that is as close as we would like to 3 by finding a large enough input. So the mathematical way of writing all this is that the limit as t goes to infinity of the function 3 plus 1 over t is equal to 3. We could have also gone for a limit at negative infinity, and then we have a similar thing, and it is also equal to 3. So we say that the limit as x approaches infinity of f of x is L, written this, if x of f of x is defined for some interval a to infinity, and the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large, or far enough to the right. We will often call it the limit at infinity, or the limit to infinity, or to negative infinity if we're doing that instead. So here's some examples. So in this first example, the function, so in all of these examples, we have that the limit as x goes to infinity of f of x is L, where L is the value of the blue line. And here f of x just approaches it from beneath. In the second example, we have the squiggly red line, where we see that as it goes to the right, as we take values farther and farther to the right, the function gradually settles down to being closer and closer to the blue line. And we can imagine if we went sort of infinitely far out, it would actually just become the blue line. And in the third case, this blue line will be what's called a horizontal asymptote, but this is an example where, the function crosses the horizontal asymptote, and of course this one above it was an example of that as well. Okay, so in each of these cases we had the limit of x goes to infinity of f of x was L. So it is possible for a limit at infinity to not exist. An example of that would be, let's consider the limit as x goes to infinity of cosine of x. Okay, so now if we take a look at the cosine function, well, cosine just oscillates up and down forever. And so, if we just keep taking inputs farther and farther to the right, well, the outputs never really settle towards a single number. They just keep bouncing up and down between kind of -1 and 1, and so it never settles down to a particular number, and in that case, we say that the limit does not exist. So we've talked before about a vertical asymptote. So a vertical asymptote is when, if the input is approaching a single number and the outputs are becoming unbounded or going off to infinity, that's a vertical asymptote. A horizontal asymptote, on the other hand, is saying if we send the inputs off to infinity, is there something that the output settles towards or approaches? And so essentially, a horizontal asymptote is another word for saying that a function has a limit at infinity. So if a function has a limit at infinity or a limit at -infinity, then it's said to have a horizontal asymptote of whatever that limit's equal to. Okay. So in our kind of running example for the function f of t equals 3 plus 1 over t, we saw that the limit as t goes to infinity of this function was 3. So that means y equals 3 is a horizontal asymptote. So another thing that can happen is that as you go off to infinity, the function doesn't settle towards a single number, but it also doesn't bounce between various numbers like cosine did. So another thing that can happen is something like maybe you have x cubed. So in this case, we see that as we plug in outputs farther and farther to the right, the outputs are getting higher and higher, and they never stop going up. And we can make it as large as we want by going far enough out to the right. So in this case, we would say that the limit as x goes to infinity of x cubed, well, it's not equal to any specific number, it just keeps growing forever, and so it's equal to plus infinity. If we were to go to the left now instead, so if we were to take the limit at -infinity of x cubed, we see that as we go to the left, take inputs farther and farther to the left, the outputs are getting larger and larger but negative numbers. So those are growing downward forever, and so the limit will be -infinity. So it's possible for limits at infinity to be also equal to plus or minus infinity. And here's the technical version of that. So these will be some of our basic building blocks for understanding more complicated limits, but we want to understand what simple functions look like and how they work first, and then how to combine them later. So in the first one, this one says that if you have the limit as x goes to infinity of x to any positive power, that will always be positive infinity. And this is basically for the reason that if you take any x to a positive power and try to graph it, for example, x squared or x cubed, as we go farther to the right, these are both going bigger and bigger, and so they go off to positive infinity. Okay. And that works for, you could also do it for x to the 3/2, or x to the 9th, or x to the 1/2. The square root also does this. So those are all examples that if you take the limit at positive infinity, you get positive infinity. Things get a little bit more tricky when you're taking the limit at -infinity, because you have to worry about signs. So if we were to look at, so in this example, we see that as we go to the left, the limit as x goes to -infinity goes to positive infinity because we're squaring the negative numbers. And so this one would be equal to plus infinity, which we can also think of as being -1 squared times infinity, which is positive infinity. In the x cubed example, we see that it should be -infinity because as we go to the left, the outputs are getting more and more negative forever without bound. And so here, the limit of x cubed is the same as minus 1 cubed times infinity. So this will be minus infinity. So it turns out for limits at negative infinity of x2 powers, if the power is odd, then you'll get a negative infinity. If the power is even, you'll get positive infinity. And once in a while it won't make sense. So, for instance, it wouldn't make sense to ask what the limit at minus infinity of square root of x is, since that doesn't make sense to plug negative numbers into, right? Its graph doesn't even go to the right. So that one would not have a limit. So the third type of function is if I have the limit as x goes to either plus infinity or minus infinity of 1 over x to a positive power. So this turns out to be always 0. For example, you could consider something like 1 over x squared or 1 over square root of x. Right, so in both cases, you'll see that the limit is 0. So the limit, say x goes to minus infinity of 1 over x squared, that's 0. And essentially the reasoning here is, as we plug larger and larger numbers into 1 over x squared, well, I'm taking 1 over a very large number, and so it's getting smaller and smaller and approaching 0. We do have to be careful when we're taking limits at minus infinity that our function's actually defined for negative numbers. Like for the square root of function, our graph actually isn't defined for negative numbers, so it wouldn't make sense to take the limit as x approaches minus infinity. But if we take it at positive infinity of 1 over square root of x, this would be 0 again. So the final thing I want to mention is that most of the limit laws we had for limits hold for infinite limits as well. So for example, we can use one of the limit laws to break up this limit as limit as x goes to infinity of x cubed plus the limit of just x. And it turns out that if you add two infinities of the same sign, you get the same infinity. I'll give you a couple warnings that if you subtract, and if you end up with using the limit laws to subtract infinities, this is typically not the right thing to do because it can turn out to have many answers depending on the situation. So if you end up using a limit law that gives you a subtraction of two infinities, that's dangerous. So try not to do that. Or if you end up dividing infinities, this is also another dangerous one. If you end up dividing infinities, this is also undefined. So in both cases, they're technically undefined. You can't tell just from this process.